Good afternoon, everyone. We will take 1 more minute for other people to join before we start. Hello, I'm Claudine Hamilius and would like to welcome everyone to a new edition of our 2020 Customer Webinar Series. Today's webinar is focused on coatings. The topic of this webinar is Mastering the Efficiency of TiO2 in Coatings. Today's presenter is Dr. Steven de Bakker, Senior Innovation Consultant for the EMEA region. Before we start, I would like to share some practical information about the Q&A process. Everyone in the audience is on mute. We are recording this session and will send you an email with a link to the recording. You can post your questions anonymously via the chat box. Other participants will not see your questions. If you are not able to answer all the questions during this webinar, we will follow up with you afterwards. So it is my privilege to present Dr. Steven de Bakker, Senior Innovation Consultant, to you. Steven, the floor is yours.
Thank you very much, Claudine, for introduction. So welcome everybody today on this first part around optimization. Today we will talk about optimization of the TiO2 in coating. So we'll talk about different strategies on how that can be reached. The second part, that will be about dispersion optimization, and that will be given next month by my colleague, Gilbert Michiels. So a few words about myself. I have a PhD in organic chemistry, and I joined DuPont de Nemours in those days in 2003, so that's a while ago, as a formulating chemist for automotive coatings. About 5 years after that, I switched to the titanium dioxide department as a technical consultant, which I'm still am, and I'm still based in Belgium, from where we work. Today's agenda, we will give a few words about what makes titanium dioxide so special, not with the idea to promote titanium dioxide as such, but just to explain you what's the difference between titanium dioxide and also the extenders, what we will talk later on. We'll also talk about some fundamental mechanisms how TiO2 works, because it also explains what are the limitations of titanium dioxide. Once we understand these limitations, we can start to think on what we can do about these limitations. And then finally, we'll talk also about a new grade TS6300, which is developed for special niche applications. And of course, we come to a conclusion. But we will start with some fundamental characteristics from TiO2 and of how it works. And basically, titanium dioxide is transparent, but it scatters light. So it doesn't give the whiteness due to absorption like other pigments, but it really scatters the light. And light scattering, that's actually a combination of 3 physical processes, being reflection, refraction, and diffraction. And this is illustrated in the graph below, where we see a light beam entering the coating. In that coating, you see the white dots. This is a simplification of titanium dioxide, and you see each time that the light beam hits the titanium dioxide crystal, or actually comes in the neighborhood of the titanium dioxide crystal, it's changing slightly the direction because of the light scattering. And in the end, after hitting many particles, the light that entered the coating here will also leave the coating there, giving if all the light is, if that's valid for all the fractions of the light, there will be a white light observed and a white color observed. To start with reflection and refraction, what's that? It all starts with the titanium dioxide particle. titanium dioxide is characterized by the high refractive index of 2.7, while the refractive index of a typical binder system is between 1.5 and 1.6. And it's this difference in refractive index that is very important for the different scattering mechanisms, to begin with the reflection and refraction. So we have this particle, and if you now add the light, we see that the light that hits the surface of the titanium dioxide, so the border between the binder system and the titanium dioxide, we see two phenomena. Either the light can reflect, it doesn't penetrate in a titanium dioxide crystal. It is illustrated in this by this arrow, just reflects. That's what we call reflection. If it penetrates the titanium dioxide crystal, it will also change direction. That's illustrated here in this arrow. And also when it leaves the titanium dioxide crystal, so going through to a medium with a lower refractive index, it will change direction once more. So the overall process of hitting just one crystal is a change in direction. Important here that this mechanism, both reflection and refraction, actually plays at the interface between the titanium dioxide crystal and the binder system. Light that doesn't hit the titanium dioxide actually just goes through. That there is no interaction. There is no reflection and refraction, actually, I should say. This is illustrated, the effect of the refractive index is illustrated in this chart, where we made 5 paints, the same amount of different extenders and titanium dioxide, so 20 volume percent, in an acrylic binder system. And a typical binder system, as I said, has a refractive index of 1.6. If we make these paints, we apply the same thickness, then we see if we make the paint with only a clay, clay has a refractive index of 1.5. There is no difference between the clay refractive index and the binder refractive index, so the whole thing is actually basically transparent. The same story for the calcium carbonate. If you do repeat the experiment with zinc oxide has refractive index of 2. It starts to get opaque, but actually the only thing that really makes it opaque is titanium dioxide, and especially the rutile titanium dioxide with the highest refractive index of 2.7. There is another type of titanium dioxide, anatase, another crystal form, that has a lower refractive index, 2.5. And that's also resulting in a lower scattering power. So that's why most pigmentary TiO2 is actually from the rutile crystal form. Just illustrating the importance of refractive index here. Sometimes the difference can be small. For example, the difference between zinc oxide has refractive index of 2 and rutile titanium dioxide 2.7. So it's only quote unquote a difference of 0.7. But actually there is a exponential relationship between refractive index and hiding power. And therefore a small difference in refractive index can result in a very high difference in scattering power. And here it's calculated that at the same concentrations, the zinc oxide needs a 6 times higher thickness, so it's 6 times more material in order to come to the same opacity. That was all refraction and diffraction, a phenomenon that plays around the interface or at the interface of titanium dioxide and the binder. There is a third mechanism, and that's called diffraction. That's completely different. This is a phenomenon that plays in the neighborhood of the titanium dioxide. So no need to hit for the light to hit the titanium dioxide crystal, just coming in the neighborhood. And when does this phenomenon occurs? That's when the light comes in the neighborhood of a particle that is half of the wavelength of the visible light, then this phenomenon is getting important. So to illustrate this, visible light has a wavelength between 400 and 700 nanometers. That means if we can create particles half of that, to say between 200 and 350 nanometers, then we will have diffraction. So we see it here illustrated on the left part of the graph, where we see two light beams. The particle is half of the wavelength of the incident wave of the light, so there will be diffraction. It will change in direction. If we blow up the particle, we make it much larger, the light essentially will just pass through, will only very slightly change in direction, and it will not be efficient in scattering. As there is a distribution of wavelengths, we also need a distribution of particle sizes. Otherwise, we would, strictly speaking, scatter only a limited number of wavelengths, and we will not come to a wide coating. So, three mechanisms, very important. As the light doesn't need to hit the titanium dioxide crystal, but just enough to come in the neighborhood of the titanium dioxide crystal, actually the scattering volume is not a physical volume of the particle, but a volume which is much larger than strictly the volume of the titanium dioxide. And this is indicated here in the orange cube. Now we can calculate that about 2/3 of the light that is scattered is actually due to diffraction. And that means that this light actually never was in contact with the titanium dioxide crystal. Just to illustrate that diffraction is actually the main mechanism that scatters the light, that contributes to the hiding power of titanium dioxide. That has a very important consequence. So as long as we speak about single particle, we have very high efficiency. This efficiency remains very high if the titanium dioxide particles are very well spaced, if they are far away from each other. But if they are coming closer to each other, you see the orange cubes, they overlap, and the total orange volume is reduced. This is illustrated just with two particles. Of course, in a paint system, it's a three-dimensional system. So actually what we see with two parts repeats itself in 3 dimensions. So we see a very strong reduction of the total orange volume. So, and that results actually in a phenomenon that we call crowding. And this crowding reduces the total scattering volume, so also the total scattering power of the titanium dioxide. We look at it in a more scientific way. We plot here the scattering efficiency of the titanium dioxide as a function of the distance between the two particles. And we see when they are, say, 500 nanometers or 500 nanometers indeed, or half a micron separated, they have pretty high efficiency. But as they come closer and closer to each other, the efficiency goes down. And in this calculation, it's shown that the efficiency goes down by 20%. Just in this calculation, just to take into account two particles. So you can imagine what happens in 3 dimensions, what it does with efficiency. Of course, in the real paint system, we do not have 2 or 3 or 5 particles, but we have many, and we express this as the TiO2 pigment volume concentration. So that's illustrated here on the x-axis, where we plot the titanium dioxide pigment volume concentration. And on the y-axis, we plot the scattering efficiency per particle. And as was stated before, the efficiency per particle goes down as the TiO2 concentration increases. When there is almost no titanium dioxide, a single particle, we have a very efficient system. When we increase the titanium dioxide, the efficiency goes down. But of course, as we increase the number of particles, we have more scattering units. So if we now calculate the total scattering power, we can say that the total scattering power is the number of particles multiplied by the scattering efficiency per particle. And that goes through a maximum. So at low concentrations, we have very efficient particles, but not too much. At the other end of the scale, we have a lot of scattering particles, but with a low efficiency. And this results actually, if we combine both effects, in the middle, around 30% pigment volume concentrations for the TiO2, we typically see a maximum of the hiding power. So that means adding more titanium dioxide in such a paint system doesn't result in a higher hiding power. On the contrary, the hiding power will slow down, will go down a little bit. That's again an illustration of this crowding effect. So far, we talked, so that's about the fundamentals of light scattering. We explained why titanium dioxide is important and how it works. But of course, not all white things contain titanium dioxide. And you see here a few examples where there is no titanium dioxide involved. Nevertheless, these systems are white. So for example, we have what we call air in water or air in beer, the foam. It's pretty clear that this is 100% white, but without titanium dioxide. Also, the clouds in the sky, no titanium dioxide involved. It's just small water particles. They scatter also light. We have in the lower corner the styrofoam. That's basically air in polymer, also scattering the light. We can have air in paper. And if they have the right, if all these pores or these droplets have the right size, they can also scatter light. Just an example of we can cancel this light scattering is illustrated on the right side, where you see waxed paper. So it's actually normal paper, but all the pores are filled with a kind of wax. And because the pores are filled, they cannot scatter the light anymore, and therefore the wax paper is getting transparent. So you can think, if we want to optimize the scattering power, can we introduce air in paint? Air is still for free, so that would be a very nice way to do that. And to illustrate that, actually we can do that. We just have to play around with the pigment volume concentration and the critical pigment volume concentration. What are these terms referring to? It's the amount of extender expressed as a function of the amount of resin. So when we are at very low PVCs, here on this side of the graph, we have only a few extender or solid particles. It can be extender, it can be titanium dioxide. They are isolated, and if it's titanium dioxide, they are very efficient, but there are not too much of them. So we see a lower scattering power. If we increase the amount of titanium dioxide, hiding power goes up till a certain maximum. The crowding starts to work, and we see a decrease in hiding power till a certain point. And that point we call the critical pigment volume concentration. That's the point where it's just enough resin to fill up all the spaces between the particles, and so no leaving any room for creating pores in the system. Above the critical PVC, we add a little bit more solid particles, and that means that there is not enough resin to fill up all the spaces between these particles. And this results in pores. And these pores, if they have the right size, they also can scatter light. Exactly the same as we saw in the paper. There are also some air pores. If they have the right size, it also scatters the light. So we see actually an increase in hiding power here. What's the negative limitation of this is that at these pores, they do not contribute to the mechanical strength of the film. So typically paints formulated above the critical PVC are weaker in strength, in mechanical strength. And these pores, they also can absorb dirt. So what you will see in tests that evaluate dirt absorption, these paints will score poorer, and also in scrub resistance or in washability, these paints will score low as well. That means that high quality paints, and especially automotive industrial paints, they are formulated below critical PVC at pretty high amounts of titanium dioxide. The more economy lines of paints, lower quality architectural coatings, they can be typically formulated above the critical PVC. Though it's possible to create very high scattering paints above critical PVC while keeping still the scrap resistance okay, and also the dirt absorption okay. So that's a sweet spot that there is that you can use. But say overall, yeah, pores can absorb dirt that we just explained. How do we test that? Well, we apply the paint on a black paper, resulting in a white paint. We make the paint dirty with a special carbon gel stain, and that stain should mimic the fingerprints of dirty fingers. For example, people that have children around the sockets and are around the switches of the lights. And these are this kind of stains that we try to simulate. And then we wash the excess of stain, and then we're gonna measure how much stain was left, and that we're gonna express by measuring the color difference between the stained and the unstained area. And there's a formulation like here, the formula expressing the staining resistance. It results in a number, and it's a very severe test. So it looks maybe ugly here, but here the scoring of 0.09 is actually very good. While here the 0.34, that's a very high PVC paint. A lot of pores, that's not good. So that's effect of PVC. Also, the pores reduce the mechanical strength, and that's here illustrated in a scrap resistance test, where we apply the paint, we wipe it 200 times up and down, and then we measure how much paint is actually removed. A low PVC paint, only a little bit, low amount of paint is removed, while with high PVC paint, a lot of paint is removed, and sometimes the paint can be completely removed. So if we measure how much paint is removed, we actually have an indication of the weakness of the paint. So as what are now the pros and the cons of formulating above or below the critical PVC? For below the critical PVC, above critical PVC, of course, we can use air. So that results in a very high dry hiding, or it can result in a very high dry hiding. Air is still for free, so that lowers the formulation costs. But the negative points are typically washability and scrub, the wet hiding, because these pores need to be formed. In the wet stage, there are no pores yet, so that's not useful. Durability, chalking effects, they are pretty pronounced in the high PVC paints. Also, sometimes adhesion problems, mud cracking. As there are pores, they can pick up dirt and stains. And you only can work with low gloss paint. So if you see high gloss paint, by definition, they are formulated below critical PVC. So what can we do to optimize the efficiency of titanium dioxide or increase the hiding power? So here we did a quick search on so-called functional extenders. And what you find in marketing information very often is that you can use this or that product, and you can reduce the amount of titanium dioxide. You can replace titanium dioxide without impact on the hiding power, things like that. I'm pretty sure that you know this kind of marketing campaigns or marketing informations. Sometimes there is a nice picture here. Here it's a kind of a clay where you see the different layers, and between the layers you see some air pores, and it's claimed that these air pores, they also can contribute to the hiding power. Many variants. Here in our section here, we will discuss the main families or the main effects. Here we made a selection of 6 different types. Calcium carbonate, and we selected a very fine one, so it's also classified as a functional extenders mostly of the time. A diatomite, I think in German it's called a Kieselgur. We have calcined clay, we have a flash calcined clay, and the difference between the calcined and the flash calcined clay is that calcination, it's heating up the system, the clay, to a very high temperature, removing some water fraction, and then let it cool down. With the fresh calcined clay, it's a very fast process. So there the idea is that the water is removed, but the clay itself is only melted a little bit at the outside of the particle, and that should seal actually the pores. So the pores should be closed. So that's one of the ideas. We have the hollow sphere opaque polymers, so the organic white pigments, and we have the titanium dioxide in the end. So what we've done, we've made a little slurry from all these things, and we put a droplet of this very concentrated slurry on a black paper, as you see. And then we're gonna do a little experiment. We're gonna add water here in the first phase. The first step, just simulating what these different ingredients contribute to hiding power in the wet stage. And then in a second step, we're gonna add solvent, illustrating the effect of what these things do in the binder system. So in the dried paint, where we simulate the resin actually with a solvent, and the solvent has also a refractive index of 1.5. So it's a good proxy for the resin system. So let's see what happens. Oops. Let's try again. So what you see here, the droplet is on the extender each time and fills up all the pores in between the particles. And there is water has a refractive index of 1.3. So the difference between the refractive index of the particles and of the water becomes very small, and therefore the hiding power or the scattering is strongly reduced in each of these cases. Also here in the flash calcined clay, which is supposed to be closed pores, actually, yeah, the water just penetrates to that. The HSOP, it's a special case. So initially you will see it's still pretty white, but as we continue to look at the movie, you will see that slowly but steadily it's getting more and more transparent, indicating that actually the water is penetrating the hollow sphere plastic particle. The titanium dioxide, yeah, the water is on there, but it still remains white. Now let's see what happens if we add the solvent. So again, this is the contribution of these extenders in white paint in the dry stage. It's clear diatomite, that's completely transparent. Also the calcium carbonate and the clays are getting completely transparent. Special case here for the HSOP. Why is that? Actually, the solvent dissolves these polymers. So actually, yeah, we destroy it. So that's not a fair comparison. So we shouldn't look at that for the moment. But again, also the only thing that really remains really white is a titanium dioxide actually here, especially comparing with the other extenders, with the extenders. Note here, now here, the HSOP actually got also transparent as it was absorbing the water in the plastic beads. Okay. I'm trying to move the presentation. Oh. Okay, we're back on track. So are these extenders, these functional extenders, now really worthless, as the movie would suggest? No, not at all. It just all depends on what's your reference point, and it all depends on where you start from. Here in this case, we started from a coating in the wet stage. So the blue thing here is supposed to mimic the wet stage. Very coarse extender, very coarse calcium carbonate, and titanium dioxide particles. That's our reference system. During the drying, there is a compaction, the volume shrinks, and the places for the titanium dioxide are pretty limited because yeah, these coarse extenders, they take a lot of place. They really push the titanium dioxide together. That lowers the distance between the titanium dioxide particles, and therefore they become very sensitive to crowding. So low efficiency of the titanium dioxide. If we now replace the coarse calcium carbonate with a fine calcium carbonate, and we do it in such a way that we replace an equal volume of coarse calcium carbonate by the same volume of the fine calcium carbonate, we end up in a completely different situation. We have the same volume calcium carbonate, the same amount of titanium dioxide particles. In the wet stage, very good spacing, as was here, very good spacing. But now in the dry stage, the titanium dioxide particles have much more freedom to pick an arbitrary place. And so there is a bigger chance for having a better spaced titanium dioxide. And this is illustrated in a little experiment that we've done. So we made a paint with no titanium dioxide, so PVC TiO2 of 0, and gradually we increased the amount of titanium dioxide, and then we measured the wet hiding power, so the hiding power in the wet stage. And for each level of titanium dioxide, we made the paints with 3 different types of calcium carbonate. We have calcium carbonate of 0.8 microns, so a very fine one, a medium-sized of about 5 microns, and a coarse of about 15 microns. But you see in the wet stage, actually, there is no difference. If we look now in the dry stage, you see that there is not a bit large difference between the medium-sized and the coarse calcium carbonate, but you see for the fine calcium carbonate, there is an increase in hiding power. And important to see is that this increase in hiding power is larger at high TiO2 concentrations compared to the low TiO2 concentrations. Why is that? At high concentrations, we have a lot of crowding with the medium and the coarse ones, while the fine one, it really allows a better spacing, so less crowding, so more scattering efficiency compared to the 2 other ones. At low concentrations, actually, the difference becomes very small. What to say about HSOP? As we said, actually, it's a plastic bead, a hollow bead, which is filled with water. And during the drying, actually, the water evaporates and is replaced by air. Air has a refractive index of 1, and therefore it will also scatter light. These beads have a diameter which is optimized to scatter light around 300 nanometers. By coincidence, it's the same diameter as for functional pigmentary TiO2. But that's just actually a coincidence as a function of refractive indices. But it's the same diameter. If we use this in a coating, the same story as we told before in this kind of graphs. We have now titanium dioxide, a very fine calcium carbonate, and we replace the very fine calcium carbonate with the HSOP, same volume. We do not see any difference in the wet stage, but during the drying, actually, we expect to see some extra hiding from the air voids. An additional parameter here that's important. We talked already a few times about the importance of the difference in refractive index. What you see here in the upper part is that titanium dioxide is surrounded by binder system, so refractive index 1.5, while here in the lower example with the HSOP, the titanium dioxide is in the neighborhood of an air bubble, basically. Air refractive index of 1. So there is a very huge difference between the refractive index of the titanium dioxide and of the surroundings of the titanium dioxide. So therefore, actually, you can argue that the HSOP increases the difference in refractive index and therefore gives an additional boost to the scattering power of the titanium dioxide. If that all is true, we expect a higher hiding power for the HSOP compared to the very fine calcium carbonate. Now, let's do the experiment. And indeed, in the wet stage, we do not see a difference. Of course, we see an increase in hiding power with increasing amounts of titanium dioxide, but basically we do not see a significant difference between the very fine calcium carbonate and the HSOP. In the dry stage, however, we see a difference. We see the initial scattering resulting from the titanium dioxide, the synergy between the titanium dioxide and the HSOP, and of the HSOP itself. So the two effects count actually, resulting in an increase in hiding power. So we definitely can say that the HSOP can work in this kind of systems. So in order to wrap up, what can we do? What are the strategies to improve the efficiency of the titanium dioxide? Well, if we start with a very unoptimized system, we can replace the coarse coarse calcium carbonate with very fine ones, increasing the flexibility for spacing and for putting the titanium dioxide in well-spaced distances from each other. As a result, the refractive index around the titanium dioxide will go lower and resulting in an increase in hiding power. The other trick is to include air voids, like we did with the HSOP. And there is a third trick. We can add extenders with a very high oil absorption. And these extenders, they will absorb resin, lowering the critical PVC, therefore introducing more air pores. Again, the same story. Here we have titanium dioxide originally surrounded by other titanium dioxide, so relatively high refractive index in the direct neighborhood of the titanium dioxide. Here we have titanium dioxide surrounded by air, by resin and air, I should say. So it's a lower refractive index, so a higher scattering efficiency of the titanium dioxide. And in addition, if the air pores have the right diameter, the air pores can scatter themselves also the light. So now if we do a philosophical test, can we make paint without titanium dioxide? And we do not want to make any kind of paint. We want to formulate a high quality paint. And how do we define a high quality paint? Well, we say it should be at least a scrub class 2. That means we should have a scrub loss of 20 microns, of less than 20 microns, as measured in the ISO test methods. And we want to have at least a spread rate of 10 square meters per liter. That means it's based on also of one of these ISO standards, where we assume that we have a contrast ratio of 0.98. And then we look at how many square meters we can paint with 1 liter of paint. And here we say we want to have at least 10 square meters per liter. And we give us two options. We want to make a paint without titanium dioxide and one with titanium dioxide. The one with titanium dioxide, we call it Formulation A. And you see here, we just pick a combination where we say 15% of TiO2, 16% of resin, some calcium carbonate, some other stuff, and we have indeed a hiding power of 10 square meters per liter, and we have a scrub resistance of 19 microns. So, okay, we have our high quality paints, and depending on the other parameters that you want to bring in line, there are many, many options to do it. Now, can we come to the same performance without titanium dioxide? So here, no titanium dioxide. That shouldn't be an issue. But you see a lot of red things, and red means it goes in the wrong direction. For example, the B star goes up, so it becomes a little bit more yellow. We have here the BI, that stands for the burnishing index. So that means in this case, we started with a matte paint, but if you wash away, you rub the paint a little bit, the burnishing index goes up. That means that the matte paint becomes glossy after a while. Also, the other things like here, the oil pickup, suggesting that the pores absorb dirt and it's more difficult to wash these stains away. You see also the wet hiding power goes completely in the wrong direction. But most importantly, the scrap resistance increases from 19 microns to 300 something microns. So we need to improve the scrap resistance. How do we do that? Well, we can add resin. So that's what we do here. We go from 6% to 19%. And then indeed we can come to scrap resistance of 28 microns, not 20, but okay. It's coming in the neighborhood, but you see automatically that the dry hiding power goes down drastically. So we did many other experiments, but we didn't find a way, a combination that brought us to the same performance as the one without the titanium, with the titanium dioxide. I think that's explained here. To illustrate the performance, the one without titanium dioxide, very poor performance in the scraps, in the stain sensitivity. In this combination, it gives, say, a moderate, but definitely a much better performance compared with the without case. The scrap sensitivity, also there, I think the result speaks for itself. Here, all the paint is removed, and here, yeah, still okay. Now, can functional extenders at least partially replace the TiO2? So maybe we overdid it. We took a paint formulation and we tried to reach to the same properties. Again, you see here the numbers again. With the other extenders, we reduce the amount of TiO2 with 20%. Of course, the dry hiding power goes down, the wet hiding power goes a lot down, and here we express everything as a reference. So we give this a 1 as a reference, and we express everything relatively. So it goes down by 20%, this means. If you now try to compensate this with functional extenders, yes, we can come to the initial hiding power, but actually you see a lot of red. It all goes into the wrong direction, the other properties. Another experiment at a lower titanium dioxide level, initial level, but basically the story remains the same. All in all, it's possible to replace an amount of titanium dioxide by some functional extender, and you even can reach equal dry hiding power, but at the cost of other very important paint properties. You can play around with this kind of games with what we call our TiPure formulator for TiPure pigments. It's a tool that we are developing. It's coming soon. So once it's online, we will inform you, and then you can play around to see the effect of replacing TiO2, of reducing TiO2, or replacing this extender with that extender. You can play around with that kind of things. Now, one last chapter. I see we are running out of time. What can we? So far, we talked about different things you can do with extenders. What about TiO2? You're listening to a webinar from a TiO2 supplier. So what can we do from our side? I will not repeat in detail the importance of the distance, but as I said, it was very important to keep the TiO2 particles away from each other. And that's what we do with our product TS6300. What is TS6300? It's a titanium dioxide grade where there is a very fluffy layer of silicium dioxide around it. So just sterically, because of this thick layer, the titanium dioxide particles, they cannot touch each other. They are separated very well. So therefore, they suffer less from the crowding effect. This is a micrograph on how they look. So it's the same scale, basically. You see here a traditional type of titanium dioxide. And here, titanium dioxide is actually covered with that very spongy, fluffy layer of silicium dioxide. This fluffy layer can absorb a lot of oil or resin. That results in a high oil absorption. You see here typical oil absorption are between 14 and 16 grams of oil per 100 grams of pigment, and the TiPure TS6300 is around 36. What's the effect on this curve? That's in paints below critical PVC, the hiding power is actually lower because there is simply less titanium dioxide in the pigment. But as there is, the pigment is less sensitive to crowding, it goes down less at the higher concentrations. And the third one observation is that there is a decrease in critical PVC due to the high oil absorption. And therefore, at the same amount of titanium dioxide, we expect in paints above the critical PVC an increase in hiding power. And that increase can go up to 20–30%. So I will not discuss this in detail because of time restrictions. Just to illustrate the effect, here you see the two paints, same composition. It was a commercial paint, high quality paint, made with a universal grade of titanium dioxide. And we just replaced that universal type of TiO2 with TS6300. And we applied it at the same thickness. And you see visually, yeah, the contrast ratio is much better for the TS6300 paint. Also, after roller application, I think the differences are obvious. Here, this is after one coat, that's clear. The TS6300 panel is after two coats is really completely covering, while here there is still some black shining through. Does it always work? Well, not always. Let's find out when it works and when it doesn't work. Here we did a simulation for a satin paint. We replaced the universal at 20% of the universal grade with 20% of the TS6300 paint pigment. We kept everything for the rest the same. There is some calcium carbonate in the paint. And the hiding power actually for that satin paint goes up from 10.7 square meters per liter to 14. So here you see that, say, 30% hiding power increase at no cost of the other properties. That's interesting. So no significant effect on the scrub sensitivity. But as the hiding power is much higher, you need less paint. So also the carbon footprint of this paint goes down if you express it on a square meter that is painted basis. Then we do the same with a matte paint. Again, we have here a very simple matte formulation where we replace the fine calcium carbonate with a coarser type of calcium carbonate. 20% replacement, that's here. What's the effect? Again, we see an increase in hiding power. Scrub sensitivity, not impacted. The gloss, of course, yeah, that falls down as we are switching from the fine calcium carbonate to the coarse one. What we see typically is that there is a slight increase in gloss when switching from universal grade to TS6300. Again, a lower carbon footprint because we need less paint to paint 1 square meter per liter. And then here we have an example where we have a lower amount of TiO2, so only 5%, and the rest is yeah, extenders. Well, what we see here in this case, actually we see hardly an improvement of the hiding power. So this is an example where TS6300 doesn't work. Why is that? Because in the original paint, there is only 5% of titanium dioxide, so there is actually not too much crowding, so there is nothing too much you can optimize with this type of level, this level of titanium dioxide. Same results expressed in a graphical way. I will not discuss that into detail once more. But here we have an explanation on why we see this better performance of the TS6300 paints. What we've done is we made 3 paints, and each paint differs in extender package. So we have one paint with coarse calcium carbonate, one with fine calcium carbonate, and another with glaze. And for each paint, we replaced the TiPure R902+, which is a universal grade by the TS6300. And then we measured actually the mean pore diameter with mercury porosimetry. So we plot here the diameter of the pores versus the amount of pores. And what you see here is that we have basically two groups of pores. The first group with a diameter around 2 to 3 microns, and a second group of pores with a diameter around 300-400 nanometers. And we know that these pores with 2 to 3 microns, they actually do not scatter, they do not contribute to light. They just can absorb dirt and weaken the mechanical strength, but have no positive impact on the hiding power. Now, what you see with the 902 Plus paint, you see a lot of these large pores. And if you switch to TS6300, these large pores, they actually reduce in volume, and they are replaced with pores with smaller diameters. And these smaller diameter pores, they really can contribute to the hiding power. And therefore, this explains actually the better performance for TS6300. So there are less pores that can absorb dirt, but there are more pores that scatter the light. And that's true for the three systems that we studied with very different extender packages. So as a conclusion, we can conclude that crowding can limit the efficiency of the TiO2, thereby limiting the hiding power of the coating. We see that very often the efficiency of the TiO2 can be improved by adjusting the formulation, and that can be done by adjusting the extender package, playing around with the PVC, the critical PVC, and so on. But very often this also affects the other properties of the paint. And all these things need to be brought into balance. The other thing from our side, what can we do? Well, we have a product called TiPure TS6300, and that can significantly increase the hiding power of a paint above the critical PVC and with TiO2 levels above 12%. So this grade is very efficient at the higher levels of titanium dioxide, above 12%. At lower levels, it doesn't bring the improvement of 20-30%. And at last, we have a formulator, which is still under development. It's coming soon, which allows you to simulate the effect of changing extender packages, the amount of resin, the impact of TiPure TS6300 on your particular formulation. So with that, I think we come to the Q&A session. So Claudine, are there any questions?
Yes, Steven, thank you very much for presenting. I will start with the first question. So you mentioned a special type of extenders called spacers. Can you explain how they work?
Yep. So the spacers, actually, they work, they are very fine calcium carbonates, and very often, I will go back to the chart where we introduced that concept. Yeah, this will work, I think. Very often you see in marketing information that a titanium dioxide is surrounded by very fine extenders, and they call that kind of extenders spacers. And it's suggested that these spacers, they really sit in an, say, organized way around the titanium dioxide. And sitting around the titanium dioxide in that organized way actually should reduce the crowding, because if it's surrounded by these spacers, it's separated from the other titanium dioxide particles, and therefore it should suffer less from the crowding effect. We did quite some simulations and some investigations, and what we found actually that this organized structure around the titanium dioxide, that's a very simplified version of reality. In reality, actually, these spacers, they are just placed in an arbitrary way in the coating, and therefore, actually, the effect is far less pronounced as what is suggested by these drawings. And actually, what they illustrate is that if they see again, actually they start from a formulation with coarse extenders, where they replace the coarse extender with the fine extender, and therefore you have automatically a better spacing of the titanium dioxide. But that's basically a very simple approach, replacing coarse extender by fine extender. Hope did this an answer? Yep.
Next question, and I think that will be the last for today, given the time. Can TS 6300 be used with universal TiO2 like R902 Plus for tint strength, opacity, and dry film property optimization for paints below CPVC in the 35-55% range when TiO2 is 10%, less than 10%? No, sorry, bigger. Sorry.
Yeah, so at the higher amounts of titanium dioxide. Yeah.
Yes.
What we typically see is a kind of combination of the properties there. So it's and we can simulate that with a calculator. Actually, we can definitely follow up later on if we have the email of this person. What we see is actually that you have a kind of compromise situation between the universal and the TS6300 results. And indeed, let me think, the tinting strength will be positively impacted by the 902 plus. The hiding power, that's a tricky one, because depending on the exact formulation, I can imagine that the hiding power will be a bit lower, a bit higher, depending on the exact extender package. But it's really, that's a very tricky situation. It needs to be experimentally verified, I think. But so far we saw results in between, say, an average result between the 902 plus and the TS6300 performance there. You start to make combinations. I know it's a bit a confused answer, but maybe you can follow up in a one-on-one situation.
Yes, we will do that for sure. Stephen, I think this will be the last question then. Is the TS6300 easy dispersible, and does it contain TMP?
Good questions. It's easy dispersible, yes. What we see, sometimes it can increase in a slightly higher viscosity because of the higher surface area. So there is more possibilities for interaction with, there is more interaction with the dispersant. There is no TMP on a TS6300, so that's can be a way out in the current discussions indeed around TMP. There is one limitation with the TS6300, I would say. Sometimes the thick layer, silicium dioxide layer, can be overgrinded, so overgrinding is not an issue with a universal grade. That's really impossible. The fluffy layer, there it's possible to overgrind it, but really under quite harsh conditions. So in a normal situation, there is no risk for overgrinding, I would say.
Okay, thank you. So before we end the webinar, I would like to thank everyone for participating today. And please don't disconnect right away, because you will see a survey popping up, and we would love to receive your anonymous feedback. We look forward to having you again with us on our next webinar on October 21st. Thank you and have a very good day.